again, Mike, for this wonderful talk on the note of transitions and seeds that are already present in a way in what has come before. I suppose that this is the best lead over to conclude today's talks with the fourth speaker on the first big question we're discussing, creation, Marina Cortês. So Marina is with us from Kathmandu, and she will climb Mount Everest tomorrow without oxygen, so I've heard, and she can confirm that in a minute, I suppose. But she's also an astrophysicist who works at the Institute for Astrophysics and Space Sciences at the University of Lisbon. Before this, Marina worked in 3 continents, including National Berkeley Lab at UC Berkeley, the Perimeter Institute in Canada, and the Royal Observatory of Edinburgh in the UK. She has worked both in large observational collaborations, such as the Sloan Digital Sky Survey, and from a purely theoretical perspective. In her work, she challenges conventional notions as to the nature of time and is currently founding a new scientific field, which she calls biocosmology. This is the first bridge connecting cosmology and biology, scientific areas which were previously disconnected, through lack of a common mathematical framework and tools between the two up till now. I truly hope that today's talk about carving new paths in theoretical physics will give us some insights into her fascinating cross-disciplinary work. Of course, her work has influenced our understanding of the universe's youngest stages, the mystery of its present acceleration, and especially the fundamental nature of time itself. Marina, the floor is all yours, and thank you so much for joining us.
Thank you so much. And Nina, there's a lovely introduction. It's my privilege to be here with you today. First of all, I am grateful that I have internet. So Alexander Blum, for me, from my perspective, spoke really very important and to the point. Then I had Jean-Luc Lenners speaking, doing a lot of the work that I could do. Giving the state of the art in the cosmological community. And then, let me, oh gosh, I'm not good with the names. Oh, Alberto spoke of causality. So I don't need to introduce that as well. It's really a privilege. So having thanked you all, let's start how I would answer the question of creation. I can answer in the spectrum from positions. In one end of the spectrum, I can answer as a cosmologist. Thank you, Jean-Luc Lenners, that I don't need to answer as a cosmologist. From the other end of the spectrum, I can answer as an artist, which for me is also a very rich answer on how does creation, what is creation, how does it occur? As an artist, that is very, very interesting answer. But today we are in, philosophy. So I will, in between these two ends of the spectrum of answering as a cosmologist and answering as an artist, I can answer as a theoretical physicist, and I will try to answer as a philosopher. Now, there is a risk here in which there are cosmologists in the audience, Jean-Luc, so I run the risk of going very technical, and I ask the moderators, Nina or Mike, to stop me if I start talking very, very technically. Things like standard model Lagrangian or anything that you don't understand, just stop me and remind me that we're in philosophy. So Alex's question, are we really I took these upon our shoulders and a burden of cosmologists. Are we really cosmologists trying to answer deep questions about the universe came to be, or are we packaging the question? My answer here, it's not the cosmological community. My answer here is that we in cosmology, and I speak for myself, we are packaging the question in a very specialized language. You can answer me later, but I must stress that I am answering for myself, not cosmologists in general. And are these motivations really the driving forces, the motivations of answering how the universe came to be as deep questions? Are they the driving forces between inquiry in cosmology? And my answer is no. Again, it's my answer, and I'm not bestowing anyone in cosmology. So I was saying this, that the privilege of Jean-Luc and Alberto have answered this. Causality for me is quite important. In fact, there are, I like to speak in this road to reality in Roger Penrose's point of view. Roger finally won the Nobel Prize, and for me, he's been a guiding figure in my career. And so in my road to reality, and this links a little bit to the talk today, there's only two principles if you want to understand reality. And I would say here, as a theoretical physicist, the first principle is time ticks forward. And because there's enough theoretical physics, there has been enough theoretical physics here. I'm not going to go into that. But if you want, it goes a little bit into my work on irreversibility, and I guess Lee Smolin's work as well. The work we have done, and for example, proposing a quantum model of gravity in energetic causal sets. But this is another talk, and I don't want to waste it. My second principle as a theoretical physicist in what we need to understand reality is biology. One does not argue with with the theory of evolution. And I view it here as a theoretical physicist. I view the violations of statements made by biological evolution as we in theoretical physics view violation of the second law. I didn't put Arthur Eddington's quote here, but in physics, we view violations of the second law as that is something that deems your theory basically put in the trash bin. So I view here, this is the theoretical physics part of the talk, and I will leave this behind. But I view in my theoretical physics understanding of reality, I view violations of biology as a law or as a theory, biological evolution as violations of the second law. So in the interest of time, I'm gonna, I speak for myself. This will introduce the topic, which is understanding the cosmos and understanding creation. Theoretical physicists, we basically have infinite ambition, or cosmologists. Let me say cosmologists have infinite ambition. And I can say I have infinite ambition on what I understand cosmology explains, or what I want cosmology to be. and that is to explain everything. Usually, there are, for many theorists in cosmology, in theoretical physics, the assumption that we can eventually explain everything can come in flavors. So one type of answer is, if we had a computer big enough, we could integrate equations of motion, be them classical or Hilbert equations of motion. And I would then ask to those theoretical physicists answering that in this fashion, that we can explain very complex fields in the universe by the integration of a large number of equations of motion. I would then ask them, does this integration reach the social sciences? Could we explain the behavior of the economical market with this very integration of a large number of equations of motion? It depends again on the physicist that you encounter. And my claim is that we cannot integrate a nearly infinite number of equations of motion to predict. So Stu, who's my lovely friend, challenged me with a book that he has, but also in stating that one cannot pre-state what is the evolution, the next state in biological evolution. So basically, this means that Stu is telling a theoretical physicist with infinite ambition, that's why I made those preemptory remarks, that there is no standard model Lagrangian for biology. Now, I have infinite ambition in the description of the universe as a cosmologist, so I don't take this kindly. And particularly, Stu wrote this book. I meant to invite Stu to come today, but I didn't have time, and I lost my phone. I could call him right now so he could join, but I didn't have time. But he writes this very provocative book, saying that essentially physics ends at the point of describing our natural regime of what we can cover, and the emergence and evolution of life lay almost by definition and conclusively outside of the boundaries of theoretical physics. And this is very provocative. I really appreciate that somebody like Stu has come and said this, because it led me to create this new proposal. This is work with Lee, Andrew, and Stu. It's called Biocosmology. I am gonna give a fast introduction of it, but basically the way in which this ties to the argument of creation is, what is biology creating at every second? And more than the subject of the creation at the initial instant, or the questions of, did time have a beginning? Are there pre-universes? What is creation in the quantum gravitational regime? Today, I am interested in the challenge of describing from a theoretical physics perspective what is happening with biological evolution, with biological systems. What are they doing, and why do they seem to evade attempts from theoretical physics to describe them in our rigorous language. So this is why I chose to talk about biocosmology and this program. It is because that I think my ambition is that through trying to understand what biology is creating at each instant, I want to expand the limits of validity of theoretical physics by encompassing biology. So I like to tease Stu when I say, by saying, Stu, theoretical physics doesn't end at the boundaries of biology. We are coming over and we are planting, we are going to expand our boundaries, and we are going to start trying to describe biology from a rigorous methodological language that we are used to in theoretical physics. So I've gone a bit technical. Let me give, oh gosh, how do you, just 1 second, please. All right. So Anina already described these. Biocosmology is basically the attempt to create a common language, like a common currency between cosmology or theoretical physics and biology. And this is a talk for the lay audience, giving quantitative value for the worth of life, how much life is worth. This I'm going to describe. Jean-Luc described it. I'm not sure if we have touched upon the past hypothesis here, or the problem of initial conditions, which has dominated a lot of my thinking during my career. Basically, the answer of how did the world come to existence in cosmology ties together with many ways does the universe have today. And stop me if I'm going too technical. How many microstates are there in the value for entropy of the world today? So my dear Sol has won the Nobel Prize for dark energy. Dark energy dominates the universe, the energy budget today, and it also dominates the entropy budget. So what this means is that if we want to answer from a cosmological point of view, how the universe came to be, so the question of creation, we first have to test the entropy of the universe today, which is 10 to the 124 in natural units. I'm not going to go technical here. And then this means that the likelihood of the initial instant, the likelihood of the Big Bang, is 1 in e to the 10 to the 124 in natural. This is the likelihood in through Boltzmann equation for entropy. So for the technical audience, this is basically the number of microstates in corresponding to the macro state of the universe today. And so biocosmology starts when here we are counting the entropy of the universe today in a world, in a universe that looks like the left figure, a barren moon, and not one universe that has life. But life doesn't matter, because life is, the number of microstates in life is very small. The planet is very small, and it does not compare to the number of microstates corresponding to the domination of dark energy, the domination of the entropy of the dark energy. Plus, one does not count the microstates of life. It is really complex, and there is no language in physics that we could try to assess what is the configuration space of the biosphere. This is really the question that I want to get at. What is the configuration space of the biosphere? And it could be a Hilbert space, it could be a phase space, it could be a classical configuration space. And sorry, I've gone a little technical, but I will come back. But that's where I want to go. This is a part that just compares physics with biology. Here on the left is the standard model Lagrangian for particle physics. And basically in biology, we don't have laws, fundamental laws, underlying fundamental laws like we have for physics. So it's quite difficult to address it from a rigorous technical language. And what Stu proposed and what I am using, what we are using as a tool to start to count the number of microstates in biology is basically here combinatorial innovation. There's this equation that's called the theory of the adjacent possible that Stu created. And I can go a little bit more technical later if you want what exactly is combinatorial innovation and why can it act as something that we could call a Lagrangian for biology. This is, let me disclaim here, very, very in the most loose sense, a kind of a Lagrangian, but I'm not going to go into that right now. And what we tried to count it, or we have counted how many microstates could there be in life. So we compared to the total number of microstates in the cosmos, which do not include life. So previously we thought that the number of microstates in the biosphere was 0, and in the cosmos it is 124. And I've written here things this is meant to be for a lay audience, and we started to oh, I'm gone. Basically, I mean, we using those tools of combinatorial innovation, we were able to count the evolution in life on the planet from the first, from the onset of life on our planet, which is 3.7 billion years ago. And just because there are cosmologists here, using the best fit a set of cosmological parameters from the Planck satellite, 3.7 billion years ago corresponds to a redshift of 0.3 using the Planck satellite's best fit of cosmological parameters. So I really like this work because we interchange between being rigorous cosmologists and measuring cosmological parameters with biology and what happened at the onset of life. But using these new tools given by the TAP equation theory of the adjacent possible, we have counted essentially that there are a lot more microstates in the biosphere than there are in the whole universe. And why is interesting? Because from a global planetary point of view, in which we are currently facing climate change and the threat of our existence on the planet exists, as cosmologists, Stu, Lee, Stu Kaufman, Lee Smolin, Andrew Little, and I are coming to say that our planet, biodiversity in our planet, contains a large number of microstates, and which gives it a worth which is incomparable, even when you consider the vastness of the cosmos and the domination of the entropy by dark energy. And so I hope that what this, more than just enlarging and carving new paths in theoretical physics by extending the tools we use in theoretical physics, I hope that this message can really serve as a, to explain or to validate the climate argument by cosmologists, saying that even before dark energy, mysteries like the dark energy, the life, our little planet and our biosphere is truly important and rich, and we hope this can play a role in the debate for the sustainable existence of our species and of the planet. After we've been working on this for 2.5 years, and there's going to be a press release in the next week or so. I am currently coordinating the last few, as I try to summit Everest, I'm coordinating the last few press articles, and finally there is going to be a live press release joined by Stu in the US, by myself in Nepal, and by Andrew in Europe, and Lee in Canada. So email me at this email if you want to receive an update on when exactly but it would take place in the next week. And that's my talk. Thank you so much.